In this video, we're computing an integral by using partial fractions decomposition. And in my integrand, I noticed this rational function. The numerator is nice and simple. Thankfully, that's just a 1. And then in the denominator, it's already been factored for us, and we have an irreducible quadratic factor, and we have a repeated linear factor. So let's get right into the partial fractions decomposition proposal. First, we'll handle the quadratic term, and for that, we need to propose a linear numerator. Then, because the linear factor in the denominator is repeated, we need two separate terms to handle that. The first is a constant divided by that linear factor. The second is another constant divided by that linear factor squared. And now our job is to algebraically solve for a, b, c, and d, and we'll be able to break this integrand into these three pieces. Each of them should be relatively simple to integrate. To clean things up, we start by multiplying by the common denominator for all these fractions, and that's the same as the denominator of the original integrand. We distribute that to every term, and that cancels the entire denominator on the left-hand side. So we're left with a 1 over there. And when I distribute it to the ax plus b over x squared plus 1 term, the x squared plus 1 is going to cancel, and I'm left with an x plus 1 quantity squared. When I distribute to the second term, one of the x plus 1s cancels, but I'm still left with an x squared plus 1 times x plus 1. And then in my last term, both factors of x plus 1 cancel, and I'm left with a d times the quantity x squared plus 1. Now it's wise to go after the low-hanging fruit here, and that's any substitution I can do that's going to produce zeros in these factors. So I'm going to sub in x equals negative 1. And when I do that, my left-hand side is still a 1. But when I put in x equals negative 1 into this first piece, in the second piece, I get 0. And the d containing term is the only survivor here. So when I put in negative 1 for x squared is going to be 1. So I have a d times 1 plus 1, or d times 2, is equal to 1. And so we've picked our low-hanging fruit. D is 1/2. The rest of these have to be solved for by a more general method. So what we're going to do is expand all the terms on the right-hand side and collect all the coefficients of x cubed, x squared, and x, and all the constants, and compare on the left and right sides of the equation. And I'm going to show enough expansion here where I can start doing the bookkeeping to find these coefficients without doing a 100% complete expansion. So I'm going to at least square the x plus 1 in this first piece. That gives me x squared plus 2x plus 1. And I'll go ahead and multiply the x squared plus 1 and the x plus 1 in the second piece. It gives me an x cubed plus x squared plus x plus 1. And I'll just leave my d term alone. And so I see that the highest power of x occurring anywhere in this expression is x cubed. Like, for example, I get one here when I multiply ax times x squared. It gives me an ax cubed. I have a cx cubed happening in that second piece. So what we're going to do is compare the coefficients of x cubed on the left and right of the equation. There are no x cubes on the left side of the equation, and that means the coefficients of x cubed on the right side of the equation have to add to 0. Then we're going to do the same for x squared, and then the linear terms, and then the constants. So again, there are no x cubes on the left side of this equation. And then on the right side of the equation, I'm just going to do the bookkeeping without using a full expansion. So I look at my first expression, and I try to find, well, what's the coefficient of x cubed there? And there's only one term that's going to give me an x cubed. It's the ax times x squared. So I have an x cubed times a coming from that. And then I end up with another x cubed from this c containing term, c times x cubed. And that takes care of all the coefficients of x cubed. So a plus c must be equal to 0, and I'll write that down as my first equation. Then we move to the x squared terms, and I can get one of those out of my first product by taking ax times 2x. That gives me 2ax squared, so I have a 2a in front of an x squared. I can also get one of those by multiplying b times x squared, so I have a plus b. And then I have a cx squared happening in my second term, so I have a plus c. And then I have a dx squared. And again, there are no x squared terms on the left side of the equation, so the sum of these four constants must be 0, and I have my second equation. Then I look at the coefficients of the linear terms. On the left side, there are no linear terms, so the coefficient is 0. On the right-hand side, I get an ax multiplied by 1, so I have an ax. And then I can get a linear term out of the b by multiplying b by 2x, so I have a 2b plus 2b. The c containing term here gives me another linear term. I have a cx, so I have a plus c in these parentheses. And there are no linear terms in the d part. So this means a plus 2b plus c is equal to 0. Finally, I compare the constants on the left and right hand sides. And the constant on the left hand side is 1. And on the right hand side, from my first term, the only constant I'm going to get is a b times 1 or a b. From the c containing term, I get a plus c. And from the d containing term, I get a plus d. So I arrive at a fourth equation, b plus c plus d is equal to 1. So now we have a system of 4 equations and 4 unknowns. And don't forget, we've already solved for one of these unknowns, and that should allow us to streamline things a little bit. And these can usually be handled by just doing clever substitutions. You don't necessarily need to do something more formal, like setting up a matrix to solve the system. And out of the first equation, I'm just going to mess with that for a second. I see that a is equal to negative c. And then I start focusing on the last 2 equations. I already know d. And if I can write a in terms of c, that would give me 2 equations and 2 unknowns in terms of b and c. So I go to work on those 2. And I'm going to sub in a equals negative c into this third equation. This gives me negative c plus 2b plus c is equal to 0. And here we got extra lucky because the c's are going to cancel out. And I immediately find that b is equal to 0. So now we have 2 out of the 4 undetermined constants. Then I'll go ahead and sub into the last equation. And I have b plus c plus d is equal to 1. Well, b is 0 plus c plus d, but we already know d, that's 1/2, is equal to 1. And this is guessable. C is equal to 1/2. And now I have 3 of my undetermined constants. And now I'll go back to that first equation where I said a is equal to negative c. So apparently a is equal to negative 1/2. So now we go back to our partial fractions proposal. We proposed that our original fraction could be broken into 3 different fractions, and we solved for all those constants to show that it could be done. And now if I just sub those constants in, I've broken the integrand into 3 pieces. So a is negative 1/2, and I end up with a negative 1/2 x. b is 0, so that's that entire numerator for the quadratic factor. And the reason that piece is easy to integrate is that I see the derivative of the denominator in the numerator within a constant multiple. So I need to get a 2x up there in order to integrate it, and I'll just do that in the next step. In my second term, I have a c, that's 1/2 over x plus 1. And if I just go ahead and pull the 1/2 out in front, the integral of 1 over x plus 1 is just the natural log of the absolute value of x plus 1. And then in my third term, I have a d, which is 1/2 over x plus 1 squared. And so we can think of that term as x plus 1 to the negative 2. And the derivative of that inner function x plus 1 is just 1. And so we're able to quickly guess the antiderivative of that term. So I'm going to write one more step where I'm sort of preparing myself to guess antiderivatives. And in that first piece, what I want is a 2x in the numerator. So I'm going to multiply by 2 and divide by 2. My fraction becomes a negative 1/4 out in front. And I get a 2x in the numerator, x squared plus 1 in the denominator. So now I see the derivative of the denominator sitting in the numerator, and I know this integrates to a natural log. In the second term, I just pull the 1/2 out in front, and I have a 1 over x plus 1, which integrates to a natural log. And in my third term, I'll just pull the 1/2 out in front and re-express this as a negative exponent, x plus 1 quantity to the negative 2. And the derivative of that interior function, again, is just 1, so we don't really have to worry about the complications caused by the chain rule here. So now I guess antiderivatives. And in my first term, the negative 1/4 is a spectator, and I get the natural log of the absolute value of that denominator. Well, the denominator is guaranteed to be positive, so let's just drop the absolute value signs and write natural log x squared plus 1. Then in my second term, again, I have the derivative of the denominator sitting in the numerator. That's just 1. I get natural log absolute value x plus 1. In my third term, I just use the power rule on this, and I get x plus 1 to the negative 1 divided by negative 1. I'll go ahead and put that minus sign out in front here. And my x plus 1 to the negative 1, well, that's just the x plus 1 in the denominator. And don't forget to add your arbitrary constant plus c, and we're done with the integral. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.